Okay, in this video we're going to look at high order linear ordinary differential equations with constant coefficients. Before you continue with this video, I think it's going to be advisable to watch our video on second order linear ODEs with constant coefficients. So second order linear ODEs. Something else that's going to be useful to revise is what we call the rational root theorem of polynomials. Okay, so rational root theorem of polynomials. So again, if you want to check our video on rational root theorem of finding or factorizing polynomials and finding roots of them. All right, so here back to the matter of ODEs, we are now going to consider the linear ODE of the form, of the form an nth order derivative of y plus an minus 1 n minus first order derivative of y, and then this is going to go on and on and on, and then plus a1 y prime plus a0 y equal to 0. Let's call this equation 1. So where the ai are real constants, so where the coefficients ai are real constants, okay. So in a similar fashion to what happened with the second order ODE, which we demonstrated in that video, the auxiliary equation of the ODE number 1 is simply going to be given by a n r to the power n plus a n minus 1 r to the power n minus 1, a n minus 2 r to the power n minus 2, and so on and so forth, plus a1r plus a0 equal to 0. Let's call this one equation 2. And so the exercise of finding a solution for 1 is going to reduce to really finding the roots of this polynomial of degree n. So that's when the rational root theorem that we talked about is going to come in handy. All right, so let's look at some examples. All right, so suppose we have these ODEs that we want to solve. In A, we've got an ODE of order 3, and then the rest of them are ODEs of order 4. In all cases, they are linear, there are no initial or boundary conditions. So in all cases, we're just going to be finding the general solution. So let's get going with the first one. So we have got 2y triple prime plus 3y double prime minus 11 y prime minus 6y equal to 0. So the auxiliary equation is going to be given by 2r cubed plus 3r squared minus 11r minus 6 equals to 0. Okay, so here by the rational root theorem, the possible roots of this equation are going to be the factors of 6, which is 1, 2, 3, and 6, and also these divided by 2. So one of them is going to be plus or minus half. 2 over 2 is 1, which you already have. Then it's going to be 3 halves, and then 6 over 2 is 3, which you already have. So what we want to do is just for a moment, I'm going to call this P of R. I'm going to use the remainder theorem to try each one of these. P of 1 is just going to be the sum of the coefficients here. 2 plus 3 minus 11 minus 6, that is not equal to 0. That means 1 cannot be a root. Then P of minus 1 is going to be minus 2 here, plus 3 plus 11 minus 6, this is still non-zero. Then P of 2 is going to give us 16, going to be 8 times 2, plus 4 times 3 is 12, minus 22 minus 6. These two add up to 28, those add up to 28. So this is 0, okay? So this is telling us that r equals to 2 is a root, and r minus 2 is a factor of that polynomial we're dealing with there. So using synthetic division, we can divide. So if we put 2 there, then coefficients are 2, 3, minus 11, and minus 6. Bring 2 down. So that's going to be 7. That's going to be 3. And that's going to be 0. So what this means is that the polynomial we can write as r minus 2 into 2r squared plus 7r plus 3. This we can factorize now. It's a quadratic. If we put 3 here and 1 here, this thing works out nicely. So that tells us that our roots are going to be r1 is 2, r2 is minus a half, and r3 is negative 3. And so the general solution is going to be AE to the 2x plus BE to the minus x on 2, CE to the minus 3x. Okay, so that brings us to the end of the first example. The second example, we've got an ODE of degree of order 4, I beg your pardon. So the auxiliary equation is going to be r to the power 4 minus r cubed minus 2r minus 4 equal to 0. The possible roots this time are just factors of 4. Okay. Did I miss something here? Yeah. So here these are, so by the rational root theorem, these are the possible rational roots. Okay. So this time the possible rational roots plus or minus 1, plus or minus 2, plus or minus 4. So let's try with, start with 1. Just add the coefficients here. We have 1, minus 1, minus 2, minus 4. So by the remainder theorem, if 1 is a root, then we must get 0 here. We're not getting 0. So 1 is not a root. Then we go to negative 1. Negative 1 is going to give us 1 plus 1 plus 2 minus 4. And this works out to 0. So that means negative 1 is a root. And so we can use synthetic division to divide this polynomial by r plus 1. So we're going to have 1, that's degree 4, degree 3, degree 2, degree 1, and degree 0. So that's the coefficients. So minus 2, minus 4 here, and 4 there. Okay, so if so what this thing is telling us is that the polynomial we can write as r plus 1 r cubed minus 2r squared plus 2r minus 4. Okay, since the constant term is still 4, it means the set of possible roots for this polynomial here, let's call it PR for reduced, is still the same as before. It means plus or minus 1, plus or minus 2, etc. Okay, now if you just add up the coefficients here, you're going to see that 1 is not going to work out to 0. And then if we try negative 1, we're going to have negative 1 minus 2 minus 2 minus 4. Again, this is not giving us 0. So we continue to 2. For 2, we're going to have 8 minus 8 plus 4 minus 4. This one is 0. So that means this thing here is divisible by r minus 2. So we use synthetic division again to find the quotient. So 1 minus 2, 2 minus 4 here, which are the coefficients of this. Yeah, of course, please do have a look at our video on synthetic division if you are not up to speed with this type of thing for the So that means this polynomial we can now write in terms of r plus 1, r minus 2, and then it's going to be r squared plus 2. Okay, if we equate this to 0, it tells us that the roots are going to be r1 is negative 1 from this vector, r2 is 2 from this vector, and then r3 from this one we are going to have root 2i and minus root 2i. Okay, so the general solution is going to be ae to the minus x, be to the 2x, and then we're going to have c sine root 2x plus d cosine root 2x. Okay, at this point we are going to give you an opportunity to have a go at the last two here. I just want to go through C and D. You can pause the video, and then when you press play, then you can compare your answer with our answers. Alright, we now hope that you have done C and D. I'm now going to scroll down to our solutions here. Alright, so for C, we have got fourth order derivative of y minus 3 times y double prime minus 4y equal to 0. So the auxiliary equation is going to be r to the power 4 minus 3r squared minus 4 equal to 0. Here we have got only the even powers. Okay, whenever you've got the even powers only, it means we can treat this as a quadratic in r squared. So if we do that, we can say that we can factorize it as r squared minus 4 into r squared plus 1. Then this we can solve, equate this to 0. You get r is 2 and minus 2. Equate this to 0, you get I and minus I. And so our general solution is going to be ae to the 2x corresponding to the first one, plus be to the minus 2x, plus c sine x, plus d cosine x. So that's going to be our general solution. For D, we've got a fourth order ODE. Again, the auxiliary equation is going to be r to the power 4 minus r squared plus 2r plus 2 equal to 0. Notice that in this case, because of this term, we can't approach that quadratic approach. We can't use that quadratic approach that we use there. So we just have to go through the rational root theorem. Since the constant is just 2, then either plus or minus 1 or plus or minus 2 are the possible roots. If we plug in 1 here, we don't get 0. But if we plug in negative 1, we get 0, which means negative 1 is a root. And so using synthetic division, we find that we can write that polynomial as r plus 1 into r cubed minus r squared plus 2. Okay, we now call this one PR for reduced. The constant is still 2, so which means this is still our set of possible roots. Now you're going to see that if we just add the coefficients here, which is what P of PR of 1 is, we don't get 0 because it's 1 minus 1 plus 2, so that is not going to be 0. But if we plug in negative 1, then all of a sudden this one is going to be, so it's negative 1 minus 1 plus 2, which is 0. So that means this is divisible by r plus 1 again. So then we use synthetic division, we reduce it. So we find that that polynomial we can write as r plus 1 into r plus 1 into r squared minus 2r plus 2. This we can solve using the quadratic formula. But if you just quickly check the discriminant, you're going to find that it is negative. It's going to be 4 minus 8, which is negative 4. So if it's negative, it means that the roots are not real, and indeed the roots are 1 plus I and 1 minus I. So a negative 1 is a repeated root. So that means our general solution is going to be so we're going to have e to the minus x plus bxe to the minus x. So that's just from this one, because it's repeated. Then we're going to have e to the x, because here alpha is 1. So e to the x, then c cosine x plus d sine x. And so this is going to be our general solution for that fourth order ODE. Okay, thanks for watching. Hopefully this was useful. Do subscribe so that you can get notified when we post new material, especially if this was useful for you.